Picture this. The year is 1899, the 25th President William McKinley is in office, the world population is only 1.65 billion, and soon alcohol will be prohibited. The recent rise of the automobile has made the necessity for better roads apparent. Better roads means new infrastructure. A great example of infrastructure built during this time is located in East Montpelier, Vermont, where a group of local builders constructed a box culvert beneath Center Road in 1899. Dry masonry techniques and granite sourced from nearby adamant quarry were used to create a structure that allowed Mallory Brook to flow under the road without interruption. The initials of the builders were inscribed on the lintel and can still be seen today. Unfortunately, increasingly frequent storm events have had major impacts on Vermont's waterways and have forced the replacement of historic culverts throughout the state. As a consequence, Vermont has been losing landmarks that add to the rich history and culture of its rural landscape. It's this history that we are trying to preserve.
Despite its age, the Mallory Brook Culvert has remained intact for the last 115 years, withstanding the floods of 1927 and Hurricane Irene in 2011. However, in 2008, the Vermont Agency of Transportation, or VTrans, deemed the culvert hydraulically inadequate. The state's proposal to replace the existing structure with a modern box culvert was denied due to its historical significance. The main goals of this project were to digitally preserve the existing culvert and to explore and assess a number of potential design solutions that strike a balance between sustainability, compliance with aquatic organism passage, scour control, hydrological adequacy, and historical preservation. The first step in this process was to investigate the Mallory Brook watershed, which was determined to have an area of 1.1 square miles. Forest and pasture land are the dominant land cover types in the watershed, with some residential and agricultural land use. There are Class II wetlands adjacent to Mallory Brook that extend from the upper reaches of the watershed to the culvert. The values for the design flow rates were determined using the USGS StreamStats software. Spatial coordinates were entered into the software interface, which used regression equations to determine flow rates for the 25-year and 100-year storms. In order to verify these flow rates, a rainfall analysis was conducted with rain gauge data from nearby St. Johnsbury, Vermont. This data was fit to a probability distribution in MATLAB to obtain a 25-year rainfall depth, which was applied to the watershed in a HydroCAD model to produce a 25-year flow rate. The results of the hydraulic analysis show that the culvert must be able to handle 160 cubic feet per second of flow, which translates to a required waterway opening of approximately 21.5 square feet. Currently, the Mallory Brook culvert is 5 feet tall and 32 inches wide, with a cross-sectional area of 13 square feet and can handle a peak flow of 99 cubic feet per second. Once the flow of the brook was known, multiple design alternatives were studied. The 6 options investigated were do nothing, upstream flow mitigation, downstream flow mitigation, expansion of existing structure, complete replacement, and addition of a bypass culvert.
Capital costs for each alternative were calculated and divided into engineering support, site preparation, installation, materials, and site improvements. These cost estimates include a contingency factor of 1.2 and are based off of prices provided by VTrans, the Community College of Vermont, and SD Ireland. The recommended design is the installation of a 4-foot diameter concrete pipe adjacent to the existing culvert. Sills will be placed at 8-foot intervals in the pipe to retain natural streambed material. The total waterway area provided by this solution is 26 square feet. The addition of a bypass culvert is hydraulically adequate, preserves the historic culvert, and is less expensive than a modern replacement. The only potential drawback of this design is the possibility for erosion between the two structures during large storm events. A ground-based light detection and ranging, or LiDAR sensor, was used to create a 3-dimensional digital model of the culvert and the surrounding area. This 3D model is precise within millimeters, which allows for the visualization of fine details, including the carvings on the lintel. Regardless, if our recommended design is implemented or if VTrans goes ahead with their proposed replacement, the culvert is permanently preserved.
We would like to give a special thanks to everyone who assisted with our project. Thank you to Arnie Bombleys, Andrea Pierce, and Mondar DeWolkar for their advice and guidance. Thank you to Brennan Gauthier for bringing this subject matter to our attention. Thank you to Leslie Russell, Ian Adams, Louis Borey, and Susan Jones for their professional advice and assistance. Thank you to Dr. Robert McCullough, Richard Casella, and Marianne Neighbor for their expertise in historic preservation. Also, a big thanks to Dr. Jeff Froelich for his assistance with the terrestrial LiDAR scan.